Hello everyone, welcome back. This is Engineer Sam Wasapi. So in this video, we'll be looking at a problem involving fluid viscosity. So before we begin, do not forget to like and subscribe to the channel. Alright, so the question reads to say, two large fixed spiral planes are 12 millimeters apart as shown in the figure 2. The space between the surfaces is filled with oil of viscosity 0.972 Newton-second per meter squared. A flat thin plate, 0.25 meters squared area, moves through the oil at a velocity of 0.3 meters per second. Calculate the drag force when the plate is equidistant from both the planes and when the thin plate is at a distance of 4 millimeters from one of the plane surfaces. Alright, so now how do we go about doing this? To start with, we're going to do a little bit of some schematic to just visualize this clearly. So we have two parallel fixed planes. So let's just draw something like this and put in the other plane like that. So we know these are the fixed parallel planes. Other than that, we're having the thin plate. So let's just draw a line to show thin plate. All right, so this is our thin plate. Now, in question, as you can see, the values are in millimeters, so it's best to convert to meters. So the distance in each section, so let's call this upper part, section A, and the lower part, section B. So in section A, the distance from the thin plate to the fixed spiral plane is about 6 millimeters, and this converted to meters, we'll have it as 6 by 10 to the minus 3 meters. In a similar manner, the bottom section, the distance from the thin plane to the fixed spiral plane is the same as 6 by 10 to the minus 3 meters. The distance that we're having from one fixed plane to the other fixed plane is basically just a sum of 6 by 10 to the minus 3 and 6 by 10 to the minus 3, which tells us that the distance from this fixed plane to the other fixed plane is going to be 12 by 10 to the minus 3 meters. So this is our figure 2. Having this figure written in units that will help us calculate this, we need to remember one thing, that in question the velocity has been given to be u, which is basically our du, to be equivalent to 0.3 meters per second. Other than that, we know that we have a force going in that direction, symbolizing with a letter of a capital F. With this schematic, we can also now collect some data. We know in question, we've been told that the viscosity, which is a dynamic viscosity, mu, is about 0.972 Newton second per meter squared. Having such a unit, we need to also understand that in question, we also have the area given as 0.25 meter squared. We know that du, which is the change in velocity, is 0.3 meters per second. And lastly, dy, considering one section, is 6 by 10 to the minus 3 meters. Now, every time we're solving a question like this, the first thing we need to understand is that if we calculate the drag force in the first aspect, where they're saying when the plate is equidistant from both the plane. We're talking about when the plate has equal distance. What we have to do is to calculate one section at a time. So in numero 1, what we're going to do is calculate one section and then calculate for the other. But since it's equidistant, all we have to do is just calculate one section and then multiply by 2 to find the drag force. Now remember that the question is saying that we're having a flat, thin plate. With that in mind, whenever they say flat, thin, or use the term thin plate, we need to remember that we neglect the weight. And when we neglect the weight, it simply means that we have no buoyancy force, meaning there is no effective weight of that particular material we have in question. So, knowing this, let us now calculate one side. So let's say side A. To find the drag force, the first thing we need to calculate is basically the shear stress. Shear stress is equal to the dynamic viscosity times du over dy. Plug in the values, we know that the dynamic viscosity is 0.972 times du, which is 0.3, divided by the distance from the thin plate to the fixed parallel plane, which is 6 by 10 to the minus 3. And once you compute this, we'll have a value of 48.6 newtons per meter squared. This is correct to 1 decimal place. Now, having the shear stress, the next thing we're supposed to do is to remember that in actual sense, shear stress is equal to force over area. The force in shear stress is what we are calling as the drag force. So we know that in this question, if we make F the subjective formula, we're having the force being equal to the shear stress times the area. So if we plug in the values of the shear stress, which is about 48.6, and multiply by the area, which we did find there as 0.25, our value of the force will be a value of 12.15 newtons. And this is on one side correct to 2 decimal places. Now remember, in question it says that it is equidistance. They're saying when the plate is equidistant from both the planes. So all we have to do to find the final drag force acting on section A and B is basically to multiply the drag force from one section by 2, since the distance is one and the same. Therefore, we need to understand that the drag force is now going to be 12.15 multiplied by 2. And we have the drag force to be equivalent to 24.3 newtons, correct to 1 decimal place. So 24.3 newtons is the drag force when the plate is equidistant from both sides. I hope it is clear. Now, looking at the second aspect, second section, the question is quite different. They're saying when the thin plate is at a distance of 4 millimeters from one of the plane surfaces. If you want, you can always pause this video and try to attempt this question on your own. But with that said, let us try and do it together. So the first thing we can do is to create a schematic. Now, the way the figure has been drawn doesn't necessarily mean that you should always draw it in that way. You can actually put it in any orientation you want, so long as you can see it. If I wanted to, I can put this vertically and still apply the same concept. Let us see how we can apply the concepts. So let us try and change the orientation so that we can be familiar with any other type of problem that might be brought on such an aspect. So in my schematic for numero 2, I'll try and write it in this way. So let's have one fixed plate this side. Let's have another one on the other side. There's nothing different here. I've just put the particular schematic in a vertical position. Let us place the thin plates like that. So we know that these are the fixed parallel planes rather, and this is a thin plate. So I've been told that one side should be 4 millimeters. So if you remember, the entire distance here is 12 by 10 to the minus 3. It was 12 millimeters, but in meters is 12 by 10 to the minus 3. So if one side is considered to be 4, say this side, calling it section A, is 4 by 10 to the minus 3 meters, then what is 4 minus 12? Exactly. It's going to be 8. So we'll have 8 by 10 to the minus 3 meters on section B. Once we have this schematic, let us remember the data that we had previously. But in this case, my data will be written in form of one side. So I'll say data for side A. So for side A, the distance dy is 4 millimeters, which is 4 by 10 to the minus 3 meters. Then du is the same, 0.3 meters per second. And the area of the plate is the same, which is 0.25 meters squared. Then lastly, the dynamic viscosity, or rather just the viscosity, is 0.972 Newton second per meter squared. Now having this, the first thing we're supposed to do is to calculate the shear stress. So the shear stress is equal to the dynamic viscosity times du over dy. So shear stress is equal to dynamic viscosity 0.972 by du over dy. Du is 0.3. dy is basically 4 by 10 to the minus 3. So shear stress is now going to be about 72.9 Newton per meter squared. This is the one decimal place. So this is the shear stress on section A. But we need to calculate the drag force on section A. So this implies that the drag force, remember, will be found by relating the formula for shear stress, where we say shear stress is equal to force over area, and the force will be equal to the shear stress times the area, of which the shear stress is 72.9 times the area, which is 0.25. Computing this gives us a value of 18.225 newtons. This is correct to 3 decimal places on one side. This is side A. So once you find the drag force on side A, all you have to do next is to find the drag force on side B. So in a similar manner, we apply the same concept. So on side B, remember the value of the distance, which is dy, is 8 by 10 to the minus 3. So let's just say data. This is on side B. So we know that dy is 8 by 10 to the minus 3 meters. Du is going to be the same, 0.3 meters per second. The area is going to be the same, 0.25 meters squared. Then the dynamic viscosity also going to be the same, which is 0.972 Newton second per meter squared. Then applying a similar understanding, we say shear stress is equal to viscosity times du over dy. This is going to be the viscosity 0.972 by du, which is 0.3, and the difference in this aspect is just the distance from the thin plate to the fixed parallel planes, and in this case for section B is 8 by 10 to the minus 3. So you have the shear stress to be equal to, once we plug that in our calculators, we'll have a value of 36.45 Newton per meter squared. So this is basically our shear stress. Now, remember the question is asking for the drag force. So we'll find the drag force by relating the formula for shear stress, which is force over area. This tells us that the force is equal to shear stress times the area. So the shear stress found in question is 36.45 and the area is 0.25. So the drag force is now going to be 9.1125 newtons. This is correct to 4 decimal places. Now the number of places that you give in question entirely depends with the rules you have in your exam or tests, whatever it may be. But I guess we can find means of going around this way of rounding off. You can round off to 2 decimal places and the like. So moving on to the final aspect. Now, to conclude this, what you have to remember is that we will say therefore the drag force, okay, the drag force when the plate, excuse my handwriting, is at a distance of 4 millimeters from one of the plane surface, or the surfaces, will now be drag force, which is effective, is going to be 9.1125, which is the drag force in section B, then summed up with the drag force in section A, which was found to be 18.225. Therefore, our conclusion will be, therefore, the effective drag force is the sum of 9.1125 plus 18.225, which is 27.3375 newtons. And if I choose to round this off to 2 decimal places, this would be 27.34 newtons. So this is how we go about solving this type of a problem. So if you have any queries, you can reach out to me on WhatsApp on the line +26077149525. Remember, slow progress is better than no progress. And let's strategize for becoming a statistic. So I'll push for that A+.